Let's go over a couple of questions for this week's discussion quiz. As question 1 is multiple choice, we'll put the capital letter corresponding to our answer in this box here. Question 1 says, assume f is a polynomial. We know at -5 it's equal to -20, and at x is equal to 4, the polynomial is equal to 2. Must there be a number c falling between these two x values, such that when you evaluate the function at that number, the y value is -6? This appears to be an intermediate value theorem question. For this theorem to apply to this function, f must be continuous, and it must be continuous on the closed interval from -5 to 4. Is that true? Well, the answer is yes. Polynomials are continuous everywhere, and therefore it must be continuous on this interval. Since I know that this theorem applies, I'm going to try to draw a simple picture that illustrates what's happening with the numbers given in this problem. So I'm going to draw a very basic x, y axis and label some numbers on it. So here's my x and my y axis. The x values go from -5 up to +4. So f, the polynomial evaluated at -5, is -20. So I'll just mark that over here, and that's -20. And then if you evaluate the polynomial at 4, we're going to get 2, and I guess I'll indicate that here. The picture doesn't have to be perfect. It just has to illustrate the main highlights of what's happening on the function. Okay, this -6 is a y value, and I'm going to note that it's between -20 and +2. So I'll draw that maybe here. So we'll say like this is -6. You can think of this as like a barrier. If you have a continuous function that starts here and ends here, does it have to cross over this line? And the answer is yes, and that's what the conclusion of the intermediate value theorem is. It would look something like this. I don't know what the formula for the function is, but if it's continuous and you draw it, it has to cross over 6 at some point. And that's the number c that's being referenced in this problem. So the answer to this question is yes. And the reason for this is f is continuous. That means the intermediate value theorem does apply. Because 6, the y value, is between -20 and 2, this solution must exist. The correct answer is A, and I'll put capital A in the box. Question 2 looks like another application of the intermediate value theorem. Again, this is multiple choice, so we'll put the capital letter that corresponds to our answer in this box. Okay, first, we're told that f is the sum of an exponential function and a sine function. If we're looking to apply the intermediate value theorem, this function has to be continuous. So based on this information, is this a continuous function? Well, the sine function is continuous, exponential functions are continuous, and the sum of continuous functions is continuous. So I'm just going to simply state that f is in fact a continuous function. If the remaining hypotheses of the intermediate value theorem apply, then the answer to this question is going to be one of these yes choices. And if not, the answer is going to be no. So to figure out which category we happen to fall into, I'm going to look at the remaining information, use this to sketch a simple graph of a function to see if the answer is either yes or no. So by that I mean, I'm going to draw a simple x and y axis like this. We're told that the interval goes from -1 to x is equal to 9. So I'll put -1 here and 9 over here. Again, this doesn't have to be perfect, just has to be a simple picture. If you evaluate f at -1, the output's going to be 7. So maybe I'll illustrate that like this. And at 9, the output is 12. So that'll be, I guess, up here. And we're asking the question, is there some number c that falls between -1 and 9 such that the output of the function must be 0? Like, must this happen? And the answer is going to be no. It could happen, but it's not guaranteed to. This number, 0, is not between 7 and 12. It doesn't fall in this range. So, for example, the function could look something like this. Your function's here, it's continuous, and eventually it has to end up over here. It does not have to pass over 0. So 0, the y value, is down here. So the answer to this one is no, there doesn't have to be a solution. And the reason is 0 does not fall between 7 and 12 for a y value. So I want to choose no. Well, it's not D. I mean, I know this is a continuous function, so I'm not going to choose this one. But as 0 doesn't fall between f of negative 1, which is 7, and f of 9, which is 12, I'm going to select this as my answer and put capital C in the box. The last question, question 3, is free response, meaning we're graded on not just the answers, but also the work that we show. We're asked to find the equation or equations of any horizontal asymptotes of this function. We have to use limits to justify our answers, and we're not allowed to use L'Hopital's rule. The idea behind this is you want to consider two limits at infinity. You want to look at the limit as x goes to positive infinity of the function. If this equals a number, that number must be a horizontal asymptote. We'll do the same thing as you go to minus infinity. You may get a different number, meaning there could be potentially two horizontal asymptotes. Before doing this process, I want to note something about the function e to the x itself. E to the x approaches infinity as x approaches infinity. But e to the x approaches 0 as x approaches negative infinity. It's important to know this information about the function e to the x. But with that being said, to solve this limit, I'm going to look at the limit as x goes to infinity of, again, the same function, which I'll replace as 10e to the x plus 5 divided by 25 minus 4e to the x. The trick to solving this problem is, as we approach positive infinity, e to the x itself goes to infinity. A good strategy is, if something goes to infinity, divide every single term by that expression. So I'm going to divide all 4 of these terms by e to the x. So that is, this is the limit as x goes to infinity of, so I'm going to take 10e to the x and divide that by e to the x. I'll then take 5 and divide that by e to the x. Do the same thing for 25. And then the same thing for this 4e to the x term. Now again, this strategy only works if the thing you're dividing by goes to infinity. And I know it does because we're approaching positive infinity for x. If we simplify this, we can cancel those e to the x's and those, but we cannot cancel these e to the x's. So let's write down this expression in simplified form. Okay, so we get, well, that first fraction here is just 10. We are left over with 5 over e to the x. We're dividing by 25 divided by e to the x, and then minus 4. The thing to note is, if you divide by something, a constant, so if you divide a constant by something that goes to infinity, these go to 0. So I'm just going to note that here. This goes to 0 as x goes to infinity because you're dividing by something that's very large. And the same thing is true for this. This thing also goes to 0. This means you can actually evaluate the limit at this point. This stays 10, that stays minus 4, but as x goes to infinity, this goes to 0, and this goes to 0. We have 10 plus 0 divided by 0 minus 4. That is 10 divided by negative 4. That's a negative number. I guess you could leave it as a fraction, I suppose 5 halves. And to complete this problem, it says to express any answers as equations, not just numbers. This is a horizontal asymptote, but as an equation, you'd write that as y is equal to negative 5 halves. There we go. We also have to check to see what happens as we go to negative infinity, because potentially we could have a different answer. So I'm going to look at the limit as x goes to minus infinity of the function f of x. I think this one's going to be much simpler. And the reason is, as we go to minus infinity, e to the x goes to 0. So we can't use this trick that we did up here. This trick only worked because the thing we divided by went to infinity. This time, in this case, it's going to 0. So this is the limit as x goes to infinity of, I'm just going to copy down the function, 10e to the x plus 5 divided by 25 minus 4e to the x. And I claim that we're essentially done at this point because of the following. This and this go to 0, meaning to evaluate this limit. And I see I left off a very important thing here. This should be approaching negative infinity. Because we're approaching negative infinity, this and this just directly go to 0. This equals 0, and this equals 0. We're left with 5 and 25. So to evaluate this, this is 0 plus 5 divided by 25 minus 0, which is 5 over 25, or simply 1/5. So again, you want to state your answer as an equation, and that's y is equal to 1/5. So this function actually has two different horizontal asymptotes, -5/2 and +1/5.